Good morning, everyone, and welcome to the AmBIENCe event organized in collaboration with ENEA, Active Energy Performance Contracting in Italy. My name is Roberta D'Angiodella, Senior Communication Manager at BPI. And before giving the floor to Maria Laura Di Somma from ENEA, I will introduce you to some technicalities for the webinar. I would ask you to use the chat function to ask a content question during the sessions or to raise your hand for verbal question. In that case, I will promote you as panelists so that you will have the possibility to unmute yourself, but also to share your camera. Instead, for the technical issues or question, I would still ask you to use the chat, but I would ask you to direct all these issues to me, Roberta D'Angiodella, BPI. I also want to add that today's presentation is being recorded and will be made available within 1 week. The discussion part will instead not be recorded, so it will only the first part that will be made available. So thank you once again for joining, and I give the floor to Maria Laura, and feel free again to ask any questions in the chat.
Thank you, Roberta, for this introduction. Good morning, everybody. Very quickly, I will present myself. I am Maria Laura Di Somma, Resource Scientist and Project Manager at ENEA, the Italian National Agency for New Technologies, Energy and Sustainable Economic Development. And this morning, actually, I would like to thank you all for joining us for our Italian workshop on AmBIENCE project, where we will present, let's say, the main concept and results achieved till now in the project. The aim of the workshop is to make all of you, our national stakeholders present throughout the country, aware about the results that we achieved till now and the opportunity associated with the implementation of the active building energy performance contract, both with a view to expanding, let's say, your business, and also in terms of the potential to reduce the environmental impacts related to building consumption. The workshop today will be divided into 2 parts. So let's say that the first part will be dedicated to the discussion, the topics of the project. So we'll see the involvement of the AmBIENCE consortium, and we will present the main results achieved till now in detail. Actually, we will have, after this first introduction, we will have the introduction to AmBIENCE project made by our project coordinator, Alec Vestiau. Then I will proceed by discussing about enablers and barriers of the active building EPC in Italy. Then this presentation will be followed by the discussion on the active EPC concept and business model by our colleague Tiago Soares from InESCTech. The ABEPLAN platform will be introduced and discussed by our colleague Jeff Verbeek from Vito. Then it will be followed by Lieven Vastralen from Energy Invest, who will discuss about the active EPC market potential and outlook. And finally, we will discuss about the concept implementation in our pilots that we have in Belgium and Portugal. And this will be made by Lieven Vastralen from Energy Invest and Claire Hardy from EDP. The second part will be dedicated to the roundtable discussion with you. Actually, the main idea is to investigate the ESCO's perspective. So what is the, let's say, the perspective from national point of view, from the ESCO's on the flexibility on buildings by identifying, let's say, further barriers in addition to the ones that we've already identified, by also discussing about potential recommendations to overcome them. Actually, I would like to thank you all again, and I hope you will enjoy this workshop, and I will leave the floor to Annick. Thank you.
Good morning, everyone. I am Annick Facio, Project Manager at Vito, and we are indeed coordinating the AmBIENCE project. For those of you that are wondering, AmBIENCE is the acronym of Active Managed Buildings with Energy Performance Contracting. When we started this project, the aim was, of course, to reduce the emissions from buildings in the European Union. Of course, you can do this simply by lowering the energy consumption. but we also wanted to add an aspect of flexibility. So using electrification combined with active control. The reasoning behind this is that electrification, even for heating or hot water production, is much more efficiently. So electricity produces this heat much more efficiently and has a lower carbon intensity if it's used, of course, coming from renewable energy sources. And this way, of course, electrification reduces the emissions. As mentioned, the carbon intensity of electricity is, of course, very much linked to the renewable energy sources. So the more investments in wind, solar, and other renewable energy sources, the more the carbon intensity of electricity will, of course, drop. Very important to realize is that, of course, renewable energy sources are not available all day to the same extent. So you have variations all over the day between different days, seasons. And this makes that if we want to use these renewable energy sources and reduce the carbon intensity of the electricity, that we have to work in a smart way and be conscious of when we use and consume the energy and the electricity. And this brings me to the mission, which is to improve the economic attractiveness of building emission reduction measures by combining both the energy efficiency improvements with, of course, electrification and active control. Voilà. So what do we do in the project? As I mentioned, we are working on energy performance contracts, to which we want to add this additional aspect of flexibility. So we want to include demand response value streams in the energy performance contracts, and in this way valorize the flexibility that is available in active buildings. The classic EPC contracts are limited to most of the time larger buildings like office buildings. And the active building EPC concept we want to make available for a broader range of buildings and to clusters of buildings. You will see that in the pilot we have a house, a residential building, where we're working on this active building energy performance contract. Of course, we needed tools to forecast the demand, the value of demand response value streams in the energy performance contracting phase. And for the operational phase, we will also work on MNV methodology. In the project, we also have two pilots, a Portuguese pilot and a Belgian pilot, where we will validate the concept, the tool, and the MNV methodology. And important to know is that these pilots are real buildings where we work together with real ESCOs, really to validate all the work that we have done so far. And of course, to make sure that this active building EPC is really used, we aim to reduce the barriers and ensure applicability. And that is why we try to engage as much as possible with you, with all the relevant actors and stakeholder groups. And this is, of course, ESCOs, but also building managers, even policymakers, financial institutions, everybody who can somehow remove the barriers and move with us this step towards this introduction of the active building energy performance contracts in buildings. Now, why are we doing this? What is the impact of the project? As I mentioned, the first aim to do the project was, of course, to reduce the emissions. And we will do that by actively steering electricity consumption to times when the carbon intensity is low. Of course, if we also aim to reduce the energy costs. And this can be done by actively steering electricity consumption to times when the prices are low. Our aim was to reduce emissions by using the electricity coming from renewable energy sources, and therefore we need to leverage the value of active control of flexibility. So we will end up with lower prices and flexibility services. And of course, to have these lower emissions, we need more investments in wind and PV, and we need more demand for energy, for emission-free energy. And this we will do by offering flexibility services to deal with the generation variability and congestions. Who are the main actors that will have a benefit from our project? We have like four important actors. First, of course, the environment and the society That's quite logic. If we are able to reduce greenhouse gas emissions by electrification, by using the electricity when the carbon intensity is the lowest, there is a clear benefit for environment and society. But of course, also consumers will benefit from the project, because we will, due to these flexibility measures, we will able to shift the consumption to times where there is a lot of renewable energy and when the energy cost is lower. So there will be energy cost savings for the consumers. For the energy system stakeholders, they might have some problems with all these renewable energy sources, but adding flexibility to the system might avoid or mitigate possible problems that are resulting from the increased wind and solar energy. And of course, for the ESCO, besides the classic EPC, we offer a new product. We have this enriched active building EPC contract, which has a higher value, which is applicable to more buildings. So we actually have like a new product that the ESCOs can offer to their clients. Here you briefly see the 8 partners that are involved in the AmBIENCe project. Of course, we have ENEA from Italy, which I hope you all know. We have 2 Portuguese partners, EDP and Inerstec, 2 Spanish partners, Techniker and Seid, and then 3 partners, 3 Belgian partners, Vito and Energieinvest, and then BPIE, who is like a European institution but located in Brussels, Belgium. And I'd like to end with our work packages, the topics that we are working on in the project. ENEA took the lead to make the assessment of the energy performance contracts and buildings demand response services in Europe. And Maria Laure will also present you the barriers and enablers for active building energy performance contracts, specifically for Italy then. We also worked on the active building energy performance contract concept and the business model, which Diago will present you later. We have developed a tool, the ABEPM tool, where Chef Verbeek will give you some more information on. And finally, we also have, of course, 2 pilots, a Portuguese one that Claire Harvey will present you briefly, and then a Belgian pilot where Lieven van Stralen will give you some more information on. It was a very brief introduction. Should you need more information, you can always contact us, of course. I'd like to thank you for being here, and I'm looking forward to have an interesting discussion with you. Thank you.
Thank you very much, Annick. I will share my screen for my presentation now. I hope now you can see my screen. Okay, great. So my presentation actually discusses about the enablers and barriers for the active building EPC, specifically in Italy. I would like to start saying that in AmBIENCE project, we made a comprehensive overview of the current situation, starting from the countries represented in the AmBIENCE consortium, which are actually Italy, Belgium, Portugal, and Spain, by trying to understand which countries have the best legislative practice and offer the best environment for AmBIENCE concept and business models to succeed. And also what are the current gaps in legislation, market awareness, by also considering other factors which might have a significant impact on the successful implementation and deployment of the active building EPC that we developed in AmBIENCE. The current status of each country for implementing the active building EPC has been assessed for a set of key areas, covering aspects as ESCO, EPC status, but also demand response services and flexibility exploitation, and other factors related to the active building EPC, as, for example, the distributed energy resources flexibility assessment. This critical assessment allows the identification of the main enablers and barriers to the implementation of the AmBIENCE concept. Well, this is the situation that we found in Europe for the status of EPC ESCO and demand response services offered by buildings at a member state level. With the reference to the ESCO EPC development status, actually the assessment has been done by considering several key areas, for example, the ESCO market longevity, the ESCO relative market size, the ESCO market growth curve, and the ESCO relative market value, and the EPC market value, and the implementation of EPC in various building sectors. What you can see is that Italy is the most advanced country in the consortium. Indeed, actually, the ESCO market in Italy is still considered to be among the biggest and most developed ones in Europe. And this is mainly due to the strong legislative background established in Italy for energy efficiency in buildings. And Italy is followed by Belgium, where the energy service market is considered stable and well-sized, and by Spain. And finally, at the end of the list, there is Portugal. What about the status of explicit demand response in the countries representing the consortium? Actually, the assessment of this aspect was done by considering several key areas, as demand response access to the markets, service providers access to markets, product requirements, and measurement and verification procedures. What you can see is that Belgium is here the most advanced country in the consortium, but Belgium is followed by Italy. Actually, in Italy, the relevant regulatory framework for, let's say, exploitation, demand response, flexibility in buildings has been subject to substantial changes starting from 2017. In fact, the Italian Regulatory Authority for Electricity, Gas and Water undertook a complete review process of the ancillary service market towards an opening to the participation of new subjects by introducing the figure of the aggregator, with the aim to increase the supply of network services necessary for the national electricity system, while also integrating new subjects more and more into the electricity system. Italy is then followed by Spain and Portugal, which are left behind the other countries. But let's go into detail by, let's say, exploring the main findings for EPC ESCO market. As I said, Italy has been considered the most advanced country in the consortium regarding EPC ESCO status. The ESCO market development in Italy started from, let's say, 2004, with the ministerial decree of 20 July 2004, where a first definition of ESCO was introduced. Since then, the market actually has grown steadily and strengthened by energy efficiency certificate mechanism, which provides an important source of income for these companies. There are a lot of associations in Italy and industry groups that serve as the ESCO market in various ways. This includes also independent associations such as ASOESCO and Federesco, and also representatives of utility suppliers and technology providers. Let's consider that in 2018, the ESCO turnover from EPC amounted to 35% of total revenues. EPC are implemented in all buildings, even though their penetration is still low in some market areas. That's what we found in our critical analysis of the EPC market in Italy, sorry. And EPC are mostly used in commercial and office sector, whereas their penetration is still low in the residential sector. As for public administration, EPC were behind about 35% of the sector's energy efficiency investment. Regarding the main findings for demand response flexibility exploitation, we found that Italy is not very much advanced with the reference to the exploitation of buildings, demand response and flexibility. Indeed, actually, the relevant regulatory framework has been subject to substantial changes starting from 2017, and the complete review process of the ancillary service market can be considered still ongoing towards an opening to the participation of new subjects by also introducing the figure of the aggregator. This happened with the resolution 300 2017, which actually proposed the launch of a pilot project to test the first opening of the mercato dei servizi di dispacciamento, as well as addressing flexible electricity demand. Moreover, through this resolution, for the first time, the figure of the aggregator has been introduced, and this corresponds to the balance service provider, which is the party managing the virtually aggregated units, and is responsible for provision of services traded on the market, which is not necessarily the same as the balance responsible party. What about the main enablers for the active EPC in Italy? After this critical analysis, we considered Italy as well placed for the introduction of enhanced EPC, by considering both the key areas for the EPC ESCO market and also the potential for exploitation of demand response from buildings. What are the main enablers that we found in Italy for the EPC ESCO market? First of all, the very high competence of the ESCO. The responsibility borne, let's say, by the ESCO, indeed, through an EPC contract, all the administrative and management duties connected to energy efficiency interventions are borne by the ESCO, and this is very much appreciated by the customers. The normative obligations, for example, the preparation of audits and energy audits, which are mandatory for energy-intensive company, has led to efficiency action, in many cases carried out by the ESCO. And incentives management, indeed, the ESCO normally manage incentives and the deduction granted by law on behalf of the customer, who receives indirect economic benefits. The main enablers that we found for demand response services offered by clusters of buildings are mainly three. First of all, the ongoing revision of the regulatory framework according to the concept of technology neutrality. The second one is the ongoing revision of the regulatory framework in order to allow independent aggregators, and also the ongoing revision of the minimum performance requirements for each ancillary services set in such a way to maximize the number of units eligible to provide the service and thus to promote competition and its supply. And finally, the consumer's data availability made available through the rollout of the second generation smart meters, which represent an essential element in the full opening of the markets to new resources. But let's go into details regarding the main barriers, let's say, affecting demand side flexibility. These are the factors that we have identified as, let's say, the key factors affecting these demand side flexibility. First of all, the customer perspective, but also the market access, the design of flexibility as a product, the availability of enabler technologies, the measurement, validation and settlement, and finally, privacy and security. Regarding the customer perspective, let's say that the main barriers that we have identified are related to standardization and interoperability, but also the lack of awareness and the lack of financial incentives. And we also identified a way to make them enablers, for example, by defining use cases with the customer-centric approach, of course, by also following European legislation and European regulation regarding this, according to which actually European citizens are let's say, the main actors of energy transition, and encouraging also the interoperability to facilitate the energy management. Regarding the market access, the main barriers that we have identified are the lack of standard definition and framework for demand-side resource insight providers, for example, regarding the rules and the responsibility of aggregators and demand flexibility providers, but also the quantification of flexibility, the data sharing procedures, the conflict on remuneration among balancing responsible parties, or the integration of implicit and explicit demand response. And actually, we also identified some ways to make them enablers, for example, ensuring flexibility delivery by improving the energy management systems, or designing a framework of interactions and rules for the stakeholders, and reflect the implicit and explicit demand response on the baseline methodology. And these are, of course, some aspects that we consider in AmBIENCe project in definition of the concept and business models. Regarding design flexibility as a product, actually, we identified as a barrier the lack of definition of flexibility. Let's say the contrast between short-term and long-term flexibility, for example, the lack of a clear understanding for contribution of demand-side flexibility to the required capacity, the unclear responsibility and rules of balanced responsible parties, and actually providing proper definition through rules and regulation improvement has been considered as, let's say, a possible enabler, I mean, for overcoming these barriers. Another important aspect is, of course, the availability of technologies that allow to exploit flexibility coming from buildings. For example, lack of availability of measurement, metering equipment at building level, the lack of digitalization and ICT solutions, but also the lack of smart appliances, actually, and encouraging, for example, digitalization adaptation to customers by introducing new platforms has been considered as a possible enabler to overcome this barrier. And regarding the measurement, validation and settlement, actually we identified as barriers the methodology for creation of baseline profile, or the place of measurement, or the information exchange for verification and settlement purposes. And actually we also, let's say, identified some ways to make them enablers, for example, by providing an adequate baseline methodology for specific flexibility resources, or by providing standards for requirements for metering equipment and measurement process to enable flexibility calculation. Last but not least, the aspect related to privacy and security. Then one potential barrier is related to the consent of consumer accessing and analyzing smart meter data. And actually, of course, I mean, in order to overcome this barrier, we identified a possible enabler, for example, by providing clarification of the process of flexibility calculation and deployment. And that's all from my side. Of course, for any type of question we can discuss in the roundtable discussion. I thank you very much for your attention. And now I leave the floor to Roberta for the agenda. Thank you.
Yes, we can proceed to Tiago.
Yes. So let's start by understanding what is the classical energy performance contracting. So an EPC is a mechanism for organizing the energy efficiency financing, which provides customers with a comprehensive set of energy efficiency, renewable energy, and distributed generation measures. This contracting is often accompanied by guarantees that the savings produced by a project will be sufficient to finance the full cost of that project. A typical EPC project is delivered by ENEA and can relieve the client by proposing an optimal set of measures, giving performance guarantees for the project savings and payback time. So what is the main difference between the classical EPC and active EPC developed in AmBIENCe? Well, in a classical EPC, the focus on design is on designing and implementing various energy conservation measures to achieve the guaranteed energy consumption and cost savings, which are typically measured on a yearly basis. These include measures on regulation, recommissioning of installation, upgrades, replacements, etc. So in short, the ESCO proposes a set of energy efficiency measures and usually finance for implementing those measures. And then the customer, of course, pays a monthly fee during the period agreed in the contract. In the AEPC, the demand response and flexibility is used to change the demand for energy in time to reduce, of course, and optimize the energy costs. This can leverage price components, tariff structures, temporary storage capacity, and other demand-side parameters. So in short, the active building EPC extends the traditional EPC concept in 3 different dimensions. So the first dimension consists of extending the energy performance guarantees related to energy efficiency by including demand response service. The second dimension is to adapt the EPC to a wide range of building types. And the third dimension consists of extending the EPC to collective buildings through local energy communities. So the active EPC will give a new opportunity for buildings to become more digital and smarter. This by increasing their smart and allowing active control based on data and measurements. This active management may provide energy emissions and cost savings, and smart device with active control leveraging machine learning. Then with the addition of sensor meters and ICT, the building becomes more digital and intelligent to improve comfort and security and to support measurement and verification. So let's follow now the value chain of this EAPC. Here is the existing and new energy service value chain for the primary to the useful energy with the respective business models. Primary energy indicates the primary energy that can be saved, such as crude oil, natural gas, coal, etc. Secondary energy is the type of energy that is considered as utilities and covers electricity, district heating, and so on. And the energy supply contract is an efficient supply of final energy, such as heat, steam, or compressed air, and is contracted and measured in megawatt hours. So this model includes purchasing fuel and is comparable to district heating or cogeneration supply contracts. As for the energy performance contract, the focus is on reducing final energy consumption through energy efficiency measures such as thermal insulation and of the building and the lighting, energy management systems, etc. By adding the demand response programs and flexibility to the conventional EPC business model, the value chain can be extended toward the active building EPC. The amount of flexibility or flexiwatt hour is an important measure as it focuses on the value that is obtained from the demand response and added flexibility. This picture provides a summary of the type of demand response services that are typically offered and that deliver an increase of value to the customers, the ESCO and the utility. And the load shedding is the one requiring fewer investments, in which the main benefits are from cost reductions by avoiding higher energy price, then load shifting that can get extra benefits to the customer, and then the load shedding that requires higher smartness level on the demand side. In terms of the business model, several can be applied to the EPC. Here I present the generic business model for the AEPC, which is characterized by an ESCO delivering an active building EPC consisting of guaranteed energy cost savings based on energy efficiency and renewable energy supply measures, and of course active control of the flexibility to a customer. This beneficiary is typically the owner or occupier of a commercial, public, or individual residential building, who will compensate the ESCO for the investment through a periodic payment, including, of course, the interest. In this generic business model, the demand response is implicit, involving only the electricity supplier who supplies electricity based on dynamic tariffs. And in addition, the customer may hire the service of a facilitator to accompany him throughout the project with expert advice against the payment of a facilitation fee. Regarding the implementation of the EPC, the general procedure for the implementation is usually divided in 3 stages. So the pre-contracting, contracting, and the performance phase. The pre-contracting phase consists in identifying the potential of a project, defining the main objective of the project, and the first evaluation of the potential case. This phase has 2 main steps. The pre-feasibility that study involves the collection and analysis of data related to energy users, the benchmark of significant consumption in the facility, and development of a simple energy audit, analyzing the equipment, estimating consumption based on energy bills, etc. While the second step is the feasibility study that aims to objectively and rationally uncover the strengths and weaknesses of the existing business or proposed opportunities and threats, determining whether the solution should be implemented. Then we move to the contracting phase, which consists of the development and implementation of the project. This phase is also divided in 2 steps. The contract design, where the main calculations and quantifications in terms of the contract and shaping the features of the AEPC are performed. It includes the expected energy savings and the financial analysis. Then in the second step, there is the deployment step, where these selected design options of the project are being installed and performed. More precisely, all the equipment needed to provide control and measure the flexibility is installed in this facility. Finally, we have the performance phase. This phase refers to the period that the operational activities under the scope of the contract start until the end of the project. It is divided into 2 main steps. The operation and monitoring activities, consisting of the training of the end users and supervising the operation of the energy management plan, which this is carried out by the ESCO, and all energy efficiency and flexibility measures are monitored following an active control of the assets. Then in the last step, the model, we have the measurement and verification activities that consist of a regular measurement and verification procedure to determine the energy and cost savings that result from the implemented energy efficiency and flexibility measures. This procedure is performed along with general operations and maintenance activities until the end of the contract. Thank you. I will pass now the word to Jeff.
Okay, I'll try to share my screen first. Good morning, everybody. My name is Jeff Verbeek. I work as a researcher in the Energy Technology Department of VITO, the Flemish Institute for Technological Research, in the Algorithm Modeling and Optimization team. The title of my presentation is The ABEPM Platform, and I hope that at the end of this presentation, I can convince you that we try to make the value of demand response a bit more tangible for ESCOs. That's the subtitle of my presentation. There are 3 main topics in my presentation. First, the building blocks of ABEPM. Secondly, the energy cost cash flow sub-tool, because that's the one we consider as the most important to add demand response to the AEPC contracts. And then to make it a bit more tangible, how we did the calculations for the Belgian pilot, some preliminary results we got there. But first, the building blocks of ABEPM. Or maybe even better, what is ABEPM in the first place? Of course, it is an acronym, and the acronym stands for Active Building Energy Performance Modeling Platform. And we developed this platform with 3 goals in mind. The first goal is to calculate and guarantee operational cost savings and performance KPIs for the contract. Secondly, calculate the financial viability of a renovation. And third, update performance guarantees during the operational phase if that seems needed. We try to make the tool quite universal, and by doing so we try to support multiple stakeholder roles in the tool, typically investors, tenants, building owners, landlords, and so on. Multiple renovations, building renovations are included. Multiple demand response control strategies and multiple demand response cash flows are considered, although I have to admit that the main focus in the tool has been on implicit demand response schemes and not so much on explicit demand response. Good. This is the overview of the building blocks of the ABPM platform we developed. No panic, I'll guide you step by step through it to understand how it all connects together. First important thing is to keep in mind, I put it here at the left-hand side, it's a very data-driven approach. So it all starts with collecting lots of time series data of the building we are going to investigate, weather data, and energy consumption, time series, price information, and so on, as much as we can get. The second block is the configuration subtool. And important to keep in mind is that any calculation we do always consists of two parts. We are going to compare two things with each other. So we make a baseline configuration, typically the configuration of the building as it is today. And then we include all the renovation measures that's in the reference configuration. And then we compare them to each other to do the whole analysis. So the first step, based on these configurations and historical data from the building, we are going to create typically a building model. With a building model, I mean really a dynamic thermal building model, a simplified thermal building model, which is capable to calculate the inside comfort temperature of the user as function of time, and of course as function of the outside weather conditions and the heating put into the building, really in thermal power. We do that, we make a building model as well for the baseline as for the reference configuration. Due to the fact that this configuration file here contains all the information about the renovation, that information is also given to the financial economic calculation subtool for the investment cost calculation. The financial economic calculation subtool is the more traditional Excel sheet based evaluation tool, which is a bit more, is quite well known in financial and economic analysis. The next step is we are going to use then the energy cost cash flow estimation subtool to calculate the operational costs of the building, and we are going to do that twice. The first time with the baseline configuration and the baseline building model, we choose certain scenarios which should result in a baseline operational cost. That information is given to the financial economic calculation subtool, and it will generate a baseline KPI report. We are going to run this tool a second time, but now with the reference configuration, so the configuration we are aiming for after the renovation. That gives then the KPIs of the building after the renovation, and due to the fact this information is given to the financial economic calculation subtool as well, and due to the fact that you have them both, you can calculate the operational cost savings. Based on operational cost savings and investment costs, you can make an investment report, and financial people can get all their KPIs out of the tool, net present value, return on investment, financing, and so on. I'm not a financial expert, but I think you know what I mean. So that is the way we use the different sub-blocks in the ABPM platform. A second way we use the ABPM platform is, suppose that during the operational phase, after the renovations have been done, you know, there are discrepancies between what was estimated and and the reality. It might be that some operational conditions were a bit different, and we could rerun with the energy cost cash flow estimation subtool, do a rerun and see and correct some KPIs and correct some savings. It is a discussion which is still a bit going on between the partners, whether this is the right way to do so, because maybe it is not transparent enough for the end user, but that's something we try to figure out at this right moment. Good. So that's the top level view of the tool. I'd like to dig a bit deeper in the energy cost cash flow estimation subtool, because that's the one where we consider that makes the difference between a more traditional EPC approach and the AEPC approach we stand for in the AmBIENCe project. Okay, it is all model based, and the first thing we do is try to identify which are the relevant commodities in our simulation. Typically electricity, maybe gas, probably hot water, maybe cold water. So we have all kinds of collectors we identify, and then we are going to add little models to this matrix structure of collectors. First, we add the commodity consuming devices. For example, electricity consumption of a whole bunch of uncontrollable loads, typically in an office building it's the lighting, it's the computers which are running and so on. So background electricity consumption, which cannot be controlled in a smart way. But the building needs hot water to heat the building. Maybe hot tap water is relevant in the building. Cold water might be relevant if there is cooling in the building, and so on. So all the commodity consuming devices are added to this commodity matrix. Next, we have the commodity producing devices. In the context of buildings, that's typically only PV panels, which can produce electricity. A whole bunch of commodity converting devices might be applicable. For example, a gas boiler which converts gas into hot water, a heat pump converts electricity into hot water, and so on. CHP, air conditioning unit, and so on can be added. The next one is, and especially in the context of demand response, they are very interesting devices, are commodity storage devices. For electricity, that can be a battery. For hot water or cold water, that can be buffer tanks, which can be connected to the hot or cold water collectors. So that all together, all these individual blocks are relatively simple models, but by putting them in this matrix structure, we create quite a complex model of how all these devices interact through the commodities with each other. Of course, the building is not a standalone thing. It exchanges commodities with the outside world. So typically you have electricity grid connection. Gas you don't produce yourself, so you need to get that externally. Maybe you can even produce a bit of heat or get heat from a district heating system. Then the next step is that we are going to add cost couplings to the model. Every single connection you see in this schematic, we can connect costs to. The most obvious one are, of course, the electricity you buy from the grid, or if you inject electricity, you might get a bit of money for that too. Gas will cost you money. District heat from the district heating network will cost you money. Maybe you can inject even a bit of your excess heat and get paid for it. Important to keep in mind, the costs can be not only like the commodity costs per kilowatt hour, but also peak prices, capacity prices, and so on can be added to this model. Also important is that we can associate costs to each individual internal flow, if that's applicable. To give a simple example, it's perfectly possible that your PV panels were not financed by yourself, but a third party put them on the roof of your building, but you have to pay for the electricity you get from them. Hopefully at a lower price than what you buy from the electricity grid, but it is a possible business model in the ESCO world. So that's the cost coupling. And if you bring that all together, we have one big, what we call building and infrastructure simulation model with a whole bunch of non-controllable inputs, outside temperature, solar radiation, the uncontrollable load, and so on. We cannot control them in a smart way to make a profit or to reduce costs, but also a whole bunch of controllable inputs. And these ones we are going to use to try to get that operational cost down. And then we can calculate, of course, all the outputs of individual models, the commodity usage and the associated costs will be calculated by that simulation model. We are using that model in 3 different ways in the AmBIENCe approach. The first one is in the contracting phase. So in the energy cost cash flow estimation subtool, we use it to support the business case calculation in the ABIPAM platform. Secondly, in the operational phase, there is a possibility to use model predictive control in the smart control of the building, and then that model can be reused. And third, as mentioned earlier, in the AEPC, so in the guarantee assessment subtool, when some operational conditions have to be recalculated, the same model can be reused again to do corrections on the operational cost savings. Good. If that's still a bit too abstract, maybe it makes sense to give you a bit of an example what we did with the tool. First, I am going to focus on some preliminary results of the Belgian pilot. But first, I'd like to give you a very simple example focusing on data of 1 day to make it really tangible how we operate with this tool. We consider the following setup: electricity, hot water with a heat pump. We have hot tap water, and we have PV panels in this configuration as well. You see here the PV production for 1 day. So during the day, there is a 29 kilowatt hour electricity production by the PV panels. So it's a time series. Per quarter hour, we have the data of that. A bunch of uncontrollable load. So the uncontrollable load over the day also is time series based. You see it's a bit higher in the late afternoon and the evening compared to the night and the morning. Space heating. So the heating of the house works via the heat pump, and you see that with a very simple thermostat, you see the heating switching on and off all the time in order to make sure that the house stays at the required comfort temperature of the user. In the afternoon, it switches off due to the sunny day, and in the evening, it switches on again because it gets a bit colder again. So that's the electricity consumption due to the space heating. The hot tap water boiler, which you see here, switches on a couple of times to make sure that enough hot tap water stays available for domestic usage. And then we add an electric vehicle to it, which plugs in at some moment in time and gets charged immediately till it is full. So this is the production of this house. This is the time series of all the consuming devices. And if you bring that all together, we come to a situation, if you don't do anything smart, that a lot of the electricity production of the PV panels is just injected into the grid and not used by the local devices, which results in a typical situation where more or less 2/3 of your PV production is injected in the grid and only 1/3 is self-consumed. That's what we can call the baseline simulation. Now we are going to add smart control to the electric vehicle, the space heating, and the boiler. Of course, the production of the PV and the background consumption stays exactly the same. So you see what happens. The space heating heats just the bare minimum during the night to just reach the comfort level of the end user. And here it starts taking advantage of the excess PV production in this area to preheat the house actually, or the building, for later in the evening when the sun disappears. The hot tap water boiler does exactly the same. It makes also use of the PV production, and the EV smart charging is way better aligned to the PV production of course, this is a constructed example, but you see exactly what happens due to the fact that you do all these things in a perfect, smart way. You can avoid any injection to the grid, and you can use all your PV production locally. It's a very simplified, a bit exaggerated example, but what I wanted to make clear with this simple example is if you do not have all these time series data available, it is very, very tricky to calculate this operational cost savings for implicit demand response in a calculation tool. And that's the reason why we have a very much data-driven approach in the operational cost savings module of the ABEPM tool. To conclude, some preliminary results we achieved in the Belgian pilot case study. The situation is a bit similar as I showed before, but these are then the calculations on real data and for a whole year. So it's again electricity, gas, and hot water with a bunch of uncontrollable loads, space heating, and gas boiler. Electricity consumption, this is from a residential house where there is quite a bit of self-employed activity as well, resulting in an electricity consumption split in two zones in a time of use tariff. In the peak time about 3,000 kilowatt hours and off-peak 5,300. We used realistic thermostat settings where we keep the temperature in the building above 20.5 degrees during the day and above 15 degrees during the night. A gas boiler with an efficiency of 92% with a gas consumption of 35 megawatt hour. So that's the baseline setup, which electricity prices which are used in this simulation are 30 cents per kilowatt hour in peak and 21 off peak, 4.5 cents for gas. And that results in a yearly electricity cost of about 2,000 euro and a yearly gas cost of 1,600 euro, in total 3,671 euro. So that's the baseline calculation. The second one is where we are going to implement the envelope renovation. So we're going to insulate a house. We adapt the building model accordingly. All the rest of the settings, prices, and so on remain exactly the same, which will result, of course, in the same electricity cost, but in a reduced gas cost, leading to a cost saving, operational cost saving of 26%. The next step is the electrification and introduction of PV. We replace the gas boiler by a heat pump and PV panels are added. The 10 kilowatt peak PV is added, and we assume an injection price here of about 6.7 cents per kilowatt hour. The thermostat settings, electricity offtake, and gas prices remain identical in the rest of the calculation. And you will see that, of course, due to further electrification, the total electricity consumption goes up to 12,000 kilowatt hours per year, resulting in an offtake cost of 2,465 euro. You have a bit of an injection volume, so 4,000 kilowatt hours is injected into the grid, resulting in a total operational cost of 2,184 euro, or an additional cost saving of 20% compared to the previous situation. As in the previous example I gave, we are going to add an electric vehicle as well, which is a bit the idea of the building owner that will be in near future will be added. We assumed, and that's why I said here preliminary Belgian pilot case studies, that's not really up to date yet. We still have to recalculate these things. In this example, we assumed about 20,000 kilometers a year, a 10 kilowatt charger, and a standard kind of commuter profile. And we assume that if you don't do anything smart, you start charging straight away when you arrive at home. All the rest stays the same. So, of course, it shouldn't surprise that we have an additional electricity consumption of 3,000 kilowatt hours per year and a total cost now of about 3,100 euro a year. And now the strength of the operational cost calculation module comes forward, because now we are going to implement smart control on the heating system. So we allow the temperature in the building to vary for 1 degree during the day between 20.5 and 21.5 degrees if it is financially interesting to do so. During the night, we allow as well to preheat if that's financially interesting. The electric vehicle charging, we try to charge now at the cheap moments when there is PV injection or at low prices, and the rest stays identical. The prices stay identical. What you can see then is that the total electricity consumption goes even up a tiny bit, and that's quite a bit of a misconception. Sometimes smart control can really lead to a higher electricity consumption, and it's also in KPIs, we have to be very careful with that. But of course, now we reduced our injection volume, and the total operational cost is dropped due to the fact that we significantly reduced the injection in the grid, and the cost is further dropped due to moving some of the electricity consumption during the cheaper night tariff, reducing the operational cost with another 12.5% only due to smart control. So that concludes my part of the presentation. I hope it was a bit more insightful what we try to do in the tool, and I welcome your questions in the chat. Thank you.
Thank you, Jeff. So actually, there are a couple of questions in the chat box. I don't know if we want to address them now or maybe in the roundtable discussion.
Yeah, maybe in the roundtable discussion they will come back as well. I would leave them till the end, maybe.
Okay, great. So the floor is now to Leven.
Yes.
Okay, good morning, everybody. My name is Leven van Stralen. I am a senior partner and co-owner at EnergyInvest, one of the partners in the project, as well as president of the Belgian ESCO association called BELESCO. So I have the privilege to share you some information, partially qualified data and quantified data on the market outlook and potential for this type of business model. So I'll first say a few words about the driving forces. What is driving market potential? Try to give you some elements on that market potential itself, mainly also on the EPC markets, and then some results from the stakeholder survey, specific results, the stakeholder survey that Maria Laura also talked about in her presentation. So what is really driving the potential? It's of course the regulatory environment, as you will understand, and the capability also to access more dynamic prices. Also, of course, the current EPC and what we call maintenance and energy performance contracting market potential, particularly for ESCOs, starting from the business that they are doing today. And then there's, of course, the flexibility potential, which is at different levels, technology levels. We mentioned the heat pumps, the applications for such flexibility and the services, but also the customer acceptance. To what extent are customers, for example, accepting to have changing comfort conditions with respect to the current situation. I mentioned the dynamic prices. There's, of course, the business case comparison, and that's why the type of simulations that Jeff talked about are very important. How much of an increase and an improvement of the business cases can we expect? There is the existing aggregator market, and of course, that's more related to explicit demand response. But still, In the end, also distribution companies are interested in this flexibility and this demand response, are possibly willing to pay for it, whether it's directly or indirectly through the tariffs. And therefore, it's also important to assess that aggregator market and the new collaboration potential that could exist between ESCOs and aggregators. Ultimately, without going into detail, ESCOs could themselves, of course, become aggregators of flexibility and demand response in buildings specifically. Often today, that's targeted, of course, at the industry. And then there's the uptake of the model itself. How much interest will there be for ESCOs for this business model? And also from a facilitator, because as we know, particularly in the public sector, the facilitators are also playing a key role in putting EPC projects in the market, and that will not be different from AEPC projects in the future. If we zoom into some of those actors and what is driving for them the development for ESCOs, that's of course the improvement, as we just illustrated, of the business case for EPC, not just in the residential, but also, for example, in the commercial building sector and in the public building sector. And thus create new business opportunities in potentially also new segments. Today, we know that EPC is not commonly used in the residential housing sector. It is to some extent in social housing. So there it's also assessing how can they create services in these new segments. And then playing also a new role in this aggregation value chain and becoming themselves aggregators. For the project facilitators, it's convincing, of course, their customers and investors of alternative revenue models, and that's what we are trying to do. We are ourselves such an EPC project facilitator, and explore new advisory services, consultancy services, to explore that flexibility potential. And finally, adapting, of course, the current business models and the tendering models which we advise, which facilitators advise their customers how to tender an EPC, well, to include also how to tender to foster for AEPC contract. And then when there's specific explicit demand response, the challenge for DSOs is to unlock that untapped potential of flexibility in buildings, in addition to the one that is being addressed in industry, thus developing new relations with ESCOs who want to offer AEPC. And they're, of course, not only doing that for network capacity, but also for network resilience, and have the local uses of PV in combination, for example, with batteries at the neighborhood level to improve overall network resilience. I won't go into much detail here, but because this was shown at least to the left side by Maria Laura in her presentation. And on the right side, we have also made that assessment in the survey for other countries than the 4 countries that are in the project. Same thing for the demand response, but I just wanted to illustrate that to show how effectively, if we take both aspects and both the maturity of the EPC ESCO market on one hand, and the maturity of the flexibility markets on one hand, we see that effectively Italy and Belgium are somewhat ahead, but we see also that there's interesting potential in Spain and Portugal. That is also the purpose of such projects, is to go further in developing it. But clearly, it's the combination of EPC market potential and flexibility potential that will drive the development of the AEPC market. And we see that no country, of course, is fully green. I have some data to share to you about the status of the ESCO and EPC market. This is a generic survey done by the Joint Research Center, which is, by the way, based in Italy, as some of you may know. A lot of work being done there over the last years about the status of ESCO markets and so. And we clearly see some markets that are growing or even sometimes rapidly growing. Can be an indication that they've been a bit slow in developing. That was the case for Belgium. It's been a market that has been relatively slow to grow, where, for example, Italy has been growing faster. But we see now, since a couple of years, more rapid development. There's still large potential in many other countries. and some are stagnating or are declining. Again, this was about 2 years ago. It also shows that some of these markets are in fact cyclical, and that depending on certain conditions, they can be regulatory, they can be market actors entering into the market or leaving the market, that the market evolution is somehow dynamic. But certainly interesting to see again here that our pilot projects, and particularly Italy and Belgium countries, are still growing quite significantly. If we look at the size of the ESCO market, again here we have some conflicting sources, of course. One study from 2018 from the International Energy Agency estimating the ESCO market in Europe at around 3 billion. On the other hand, you see, and I think Maria Laura mentioned the figure of roughly 3 billion for Italy only. So probably some discrepancy in the data, but it gives you certainly a relative size compared to, for example, China, which is some extent an emerging market, but have had a very rapid development. And what's also interesting to see on the right side is how Europe has followed basically the two markets that have been pioneering performance contracting, which are Canada and the US, in the sense that there is a vast majority of projects in the public sector. And that is also the case, for example, in Belgium, and also a significant amount of projects in Italy. Whereas you see some more emerging countries, and the example is, for example, China here, but also other countries in Southeast Asia, in which the situation is completely different, and the ratio of public versus private is different. Here we also see sources from the JRC report estimating in 2015 the Italian market at about 1.5 billion. If we look at this study in more detail, here it's an estimation then for 2019 of roughly 2 billion. So it's more or less consistent, but probably means that the European market has been somewhat underestimated in the previous study. And these are some other countries, of course. And we have another study. Now we're really looking at the EPC market, and that's an important difference, because the ESCO market is much bigger and much diverser than the EPC market only. There is in some countries a significant amount of energy supply contracting. For example, in Germany, where the energy supply contracting market, and basically delivering heat, represents roughly 80 to 90% of the total ESCO market. And the EPC market, the EPC models as we know them, performance contracting renovations in the public sector and in some commercial buildings, is only representing 10%. And so here we see, for example, the Belgian market at the time only estimated at about 20 million, but the Italian market about more than 10 times bigger, roughly at 250 million. So again, that number of roughly 10% of the market in EPC from the total energy services or ESCO market. So we did also this stakeholder survey, which Maria Laura referred to. Again, I will not provide you all of course, of that information, but just a few elements to appreciate the value that stakeholders are putting into the market. And for example, when we questioned them about the interest of using flexibility in building, particularly if that would be ready to use flexibility, then 100% of the respondents said they would be interested. So, and we're talking now about mainly about the DSOs and the TSOs. So for them, flexibility at a certain rate, minimum 1 megawatt, of course, in the case of explicit demand response, they would certainly be interested in. And that also shows that for ESCOs, there is interesting potential in that market. And if we requested about the intentions, when would you start, then roughly 2/3 of them would start within the next 3 years, but almost one out of three indicated that they would start within 1 year. So again, it also showing that it's a relative priority for them. If we look at what some of the questions that we asked the flex providers, so the ESCOs, indicating what would be the driving factors for them. Then we see that roughly 1/3 it's more energy savings, and also roughly 1/3 it's more cost savings. Whereas improved comfort and the emission savings at the time were a little bit less. Although I think that if we would redo the survey today, we would probably expect the emission savings to be more important in light of the climate goals. These are some current practices. When we interrogated the ESCOs on their flexibility, there we see, of course, that passive energy measures are being used, but not so much as part of flexibility. Whereas the replacement of gas boilers by electrical appliances like heat pumps, as was illustrated in the calculations of Jeff, there we see that the majority of these type of replacements are happening up to about 50% of the cases, where this is being evaluated and sometimes even implemented. Increasing and adding storage is not so far developed yet. It's about 25% of the cases, although here we see that it's mainly in commercial buildings. And again, if you look at active and automated control, it all depends, of course, what do we put in there, because it also is today basic building management systems may be considered as being active and automated control, whereas we know now that we are looking for activating this flexibility. But at least the basic use of control is there in more than 75% of the cases, particularly in commercial and public buildings. And if we look at the technology in which active automated control is already being used today, without much surprise, that's mainly HVAC, heating, cooling, ventilation, to some extent lighting and lighting control, and then the others being less frequently, with some potential still for hot water production. And it shows clearly that we are focusing, I think, on the right technologies to be incorporated. If you look at building segments, because we can talk in general about EPC potential and flexibility potential. If we drill that down a little bit to the residential sector, with individual or collective houses or social housing, versus the more public and commercial industrial buildings, then we see, of course, a mixture of potential that today is quite low in individual private houses, which also makes the Belgian pilot not necessarily replicable as such, but it means that for such a segment, we would have to be looking at, for example, neighborhood level renovations, rather than doing them at the individual level. And the same thing for flexibility potential. So we see here that the biggest potential, without much surprise, is in public and commercial buildings. Public mainly because the EPC model is readily being deployed in the public sector, whereas the flexibility potential is similar. In the industrial buildings that are a bit out of scope of the AEPC, because we want to focus really on buildings, there we see, of course, this higher flexibility potential today. On the other hand, EPC is in any case not very well developed. These were some initial simulations done on residential buildings, of course, which will now be able to update for the Belgian pilot, for example, and other similar cases. But at the initial calculations, it already showed an increase of roughly 20% of the net present value of the project, in line with what was said before. So does this allow us to estimate AEPC market potential? Clearly it remains very difficult because the amount of variables, but I think it at least gives an indication of that potential. With the current market for ESCO services in the EU estimated at roughly anywhere between $1 and $3 billion, and probably at the high end. There is a significant potential for electrification in combination with solar, PV, and even building integrated PV. but the pace of that integration will depend on price evolutions, with these two conflicting tendencies that we see on one hand increase, on one hand decrease. The need to increase ambition levels will of course increase the need for deeper energy renovation. And we already see that happening today in EPC, where before we did projects with an ambition level of 25–30% savings. Today we see projects of 50 or 60 or 70%, and even of deep energy renovations to climate neutrality. These dynamic prices are not always available. Also in Belgium today, it's mainly night and day tariffs. There is a new capacity tariff in the northern part of the country that will probably also be introduced in the southern part of the country. But at least in a roughly 5-year time frame, we should see much more dynamic prices. The increase in the business case of 5 to 20% is certainly realistic, and that's not negligible. And it is not unlikely to our estimate that about 20 to 30% of EPC projects will become AEPC projects in the next 5 to 10 years. But this will of course depend on the capability of ESCOs to start offering them, and then secondly of also facilitators to start putting projects in the market and tendering them for their customers. And we will also survey the stakeholders in the coming months. We've done so on the regulatory environment, on the status of the market, on their current practices, but we will be surveying them in the coming months on the replication potential, looking at specific countries and see which barriers are there and how can we lift those barriers, and what is needed basically to introduce and replicate the AEPC model in the market, including of course in Italy. And I'm sure some of you will be invited to participate in this survey. And if you are interested, don't hesitate to contact us. Thank you for your attention, and maybe we'll have some more opportunity to discuss these things during the discussion session. Thank you.
Thank you very much, Lieven. Yes, just one comment from my side that we will for sure contact some of the stakeholders, for these type of surveys that we will do in next month. I think the floor is again yours, for the final presentation regarding the implementation of our concept in the pilots. So.
Yes, that's right. Thank you very much, Maria Laura. I will be going on with a small presentation. Let's see, on the Belgian pilot, and then followed by a similar short presentation from Claire on the Portuguese pilot. You already had some data from within the presentation of Jeff, but what I can do here is present you a little bit more in detail. What is the Belgian pilot really about? What is the building? How is it being used? How are we tackling that pilot? Where is the flexibility potential? And some key outputs. So the house, it's a residential house built in 1912, quite old, what we call a maison de maître. It's like a stylish building with certain architectural elements, mixing some Art Nouveau style. Quite a big house for Belgian standards, 337 square meters, which does not include the basement, which is quite large, and a double garage. Occupied by a couple and 2 dogs, ground floor plus 2 floors, meaning 1 main bedroom and 1 bathroom, because in total there were originally 4 bedrooms, but 3 of them have been transformed into an artist's working space, mainly for artistic workshops and courses. Then there's an annex that is being transformed or will soon be transformed in a main bedroom, shower room, dressing and another artistic workspace. There's also space being transformed for home offices. There is a living and dining room in the front part of the building, and the older part of the building, a small sitting room, kitchen, and an attic, which is currently not used. In terms of heating, there was originally a fuel fired boiler that was replaced by a condensing gas boiler, but there's also a wood pellet stove that was installed in 2012 for heating part of the ground floor. In terms of lighting, it's mainly LED already. In terms of the building envelope, mainly first generation double glazing, and except the home office space where windows were already replaced in the by high insulation glazing in the existing frames. The building is mainly uninsulated, so it's relatively thick, mainly brick walls. But the terrace on top of the home office space was insulated, and also the roof on top of the existing bedroom and bathroom was recently insulated and renovated, mainly because of leakages. Very important to mention is that there is a very modular use of heating and spaces in the winter period, mainly because of the large size. If the building would have to be heated at a constant temperature of 21.5 degrees, as Jeff indicated in his model, then of course that would be very expensive. So in any case, some spaces are only heated, let's say, significantly when they are being used. And that's, for example, the case for the artist workshop space, which is only used 3 or 4 days a week when there are participants basically using those. So here you see the location in Belgium, in Senef, about 45-50 kilometers south of Brussels. You see the facade with the main part on the left or middle side, and then the annex on the right side. You don't see it well here, but you see it a little bit on the figure on the bottom side, on the clear, let's say the more white roof. That's an annex that has been added in the 1970s and has served as a waiting room for a doctor's practice. And then you see on the left side, you see the heat pellet stove, and on the right side, you see the gas boiler, which was installed in 2016. Here you see some floor plans and some more indications, including a ceiling that, for example, under the terrace that has not been insulated yet, but which is foreseen in the renovation program. So flexibility potential mainly comes from electrification with the heat pump to replace this gas boiler. PV panels on the main secondary roofs and on some walls. And then the electrical vehicle that Jeff mentioned, planned for next year. For the moment, planned with what we call vehicle to load. But the idea is eventually to also have vehicle to grid capability or vehicle to home capability. The methodology, I will not go into more detail, but basically starting from defining, collecting data, an energy scan and audit was done, of course, based on theoretical assumptions. And there was a static simulation aiming at installation levels and defining the investment cost, the dynamic simulation that Jeff mentioned, and then the monitoring infrastructure that is going to be installed and studied shortly. Of course, the AEPC contract development, and then design implementing the monitoring and doing an evaluation of the lessons learned. This is a view of the energy scan and energy audit, which was done. Not go into detail. Here you see some of the results of the static simulation. All of the U and R values have been calculated, and you see the placement of the solar panels on the right side. Purpose was to target a K value of 60 for the installation, everything leading up to total investment that provides a energy saving roughly between the base case and the scenario from these 31,000 kilowatt hours to 13,000, so roughly 60% savings. And then you have the information on applying the degree days. These are all the investment details, total leading up to 85,000 euros in building envelope, roughly 20,000 in PV, and roughly 10,000 in the heat pump. This is the measurement campaign that was done, measuring temperature and in this case also heat supply from the existing gas boiler by adding some measuring equipment to the tubes, allowing to plot these heat production data points that Jeff mentioned. And so what will we have as results from the pilot? Of course, validating the EEPC business model, also defining requirements for reactive control in an energy management system. We will have the residential AEPC contract, which will not be signed within the framework of the contract, but it will at least be evaluated by some Belgian ESCOs, and it will be a template for use by others, of course. We will have a monitoring solution designed and evaluated, as well as an M&V methodology. And finally, the business case calculations using the ECFM tool and the economic and financial calculation tools will also be made for the pilot. And that's it for me. And I think it's now Claire who will provide the presentation on the Portuguese pilot.
So I will share my screen then. Okay. I hope you can see the screen.
Not yet.
Not yet.
Yes, not yet. Yes, I think. Yes, we can see it.
Yeah. Okay, perfect. Okay, yes, I will try to be quick with my presentation. I know we want to have a discussion, so last presentation I will try to go through quite quickly, and please leave any questions in the chat so we can get to them in the discussion. So I'll briefly talk about the Portuguese pilot. First of all, yeah, thanks for having me here. I'm Claire Harvey from EDP New. We're an R&D department of the Portuguese utility EDP, which operates in not only Portugal, but other countries across Europe and the world. And one of its branches is an energy retailer. And within that, they also have an ESCO service. So we're in charge of the Portuguese pilot. And a few details on the Portuguese pilot building. It's in one of our EDP headquarters in Porto, in the north of Portugal. It was built in 2011 and has no implemented EPC as of now. It's around 17,000 square meters, and that includes 10 floors, where we have open office space on floors 2 to 6. As well as this, there are some critical rooms within the building which require cooling, such as data centers on some of the floors. As well as this, it has 3 underground floors with 15 EV chargers. The building is used by approximately 600 users, and since it was built in 2011, you can see it already had some energy efficiency measures implemented in the design. So it is mainly LED lighting, which is controlled via daily schedule. They do have solar PV on the top of the building, which is pretty much all self-consumed as of now. As well as this, we have some power-driven shading blinds, which react to various environmental sensors to control these shading blinds. So about the HVAC. So the HVAC is a VRF system. So it's centrally controlled HVAC for most of those office spaces that I spoke about. And this is provided by three large chillers and a heat pump on the rooftop of the building. And there is a separate system for the data centers within the building. Also, 2 large air handling units supply these office space floors. And there's a BMS building management system and associated thermal control system in the building, which has real-time information of these indoor units, set points and temperatures, and can control these indoor units. But as of now, manually through the building operators. So yeah, the thermal control system itself, as it is right now, defines a comfort band within the office spaces. So it compares this comfort band with the real temperature in the space through temperature sensors. And then it actuates actuates the heating or cooling if the real-time temperature is out of the comfort band range, plus a small tolerance. As of now, the building mainly works in 3 levels of comfort. So you have economy, pre-comfort, and pre-comfort levels for the office spaces. So why am I discussing the ABAC so much? So that's the flexibility asset that we are studying more in detail in AmBIENCe project. So to make use of the flexibility of this HVAC system, we're basically building the models so the building can act as a thermal battery, taking advantage of the thermal inertia in the building, and basically shift the energy consumption of the heat pump and the chillers across different periods through active control, as has been already spoken about. As was also spoken about, the demand response market in Portugal. As of now, what we can do to take advantage of these of demand response is through different time of use energy tariffs. So in our pilot in Porto, we have 4 different tariffs throughout the day. So basically the HVAC will be optimized to make use of this and save money for the building owners. As well as this, we have some classic energy efficiency measures studied and associated investments and payback periods, but I'll not go into them right now, because the Porto building pilot key outputs from our demonstration will be these business models that combine not only the classic energy efficiency measures, but also this demand response flexibility measures for optimized control of the building assets, while also maintaining these comfort levels that I spoke about. Another key output from our pilot work will be detailed requirements for this active control for this operational phase to function. So software and algorithm integration. You've seen the tool from Jeff, but how this integrates into local hardware and monitoring solutions, and developments on top of building management systems to allow for this actuation of these active control measures. Another key output when we're implementing this in the pilot is the collaboration between various stakeholders. So it's not only our research project team, it's also asset management, building managers, building operators, etc., in order to realize this concept. And another key output will be this template AEPC contract, as Levin spoke about, which will include all the relevant technical clauses to be used by for the Porto building, but also as a template for our ESCO department in EDP. So I'll leave it there, just a very brief summary so that we can really get into the discussion. And yeah, thank you very much. And I guess we can move on now.
Thank you very much, Claire. Thank you very much to all speakers for these presentations. Actually, yes, as also written by Annick, a presentation